Today we're going to look at section 2.1, which is about functions and their graphs. We're going to begin with a lot of vocabulary. In your notes you should have some fill in the blanks, so as we go through just fill in the blank with each word. A relation is a mapping or pairing of input and output values. The domain is the input values. The range is the output. A function is defined as having exactly one output for each input. An ordered pair is when we put a relation in the form of x, y, where x is typically our input and y is typically our output. A coordinate plane is when we draw x and y axes, and that's how we graph our ordered pairs. It divides a graph into 4 quadrants. We start numbering them in the upper right-hand corner, and then we go around counterclockwise. So when we number out those quadrants in our coordinate plane, we see we have quadrant 1, 2, 3, and 4 in the lower right. The vertical line test tells us if we have a function or not, and it says that a relation is a function if and only if no vertical line hits more than one point. So we can look at a graph of points or lines then and decide if we have a function or not. And some of your homework problems will just be yes or no's. Is this a function or is it not? So this graph, what we do is we take vertical lines and say, is there anywhere I can draw a vertical line and hit more than 1 point? In this one, all those only hit 1 point, so that is a function. As opposed to a graph that looks like this, if I draw a vertical line, I hit more than 1 point, so that is not a function. Okay, so here we're given our input and our output. According to our definitions, our input is our domain and our output is our range. So when you're asked to list your domain and range, you're just listing the numbers of your input and output. So our domain would be -3, 1, 4. Our range would be 3, -2, 1, and 4. You can put them in numerical order if you want, but it's not really important. Then we're asked to say whether or not this is a function. The way I think about functions is like a vending machine. So in a vending machine, you decide whatever it is that you want, Snickers or M&Ms or Skittles, and you press a certain code. And when you press that code, you're putting in your input, and you're expecting to get one particular output. That's the way a function works. That when you put in an input, you should know exactly what output you're going to be getting. If there's any ambiguity, that's not good. Because if I decide I want Skittles and I press that in, I'm expecting Skittles. If I get something else, that's not really what I was planning on. So for a function, each input should be linked with exactly one output. So here, if I type in a -3, I get a 3. If I type in a 1, I'm not really sure what's going to happen. So this is not a function because there are 2 different outputs for a given input. In this one, identifying our domain and range again. Domain is the input and range is the output, so we can just list out those values. Now we have to decide if this is a function. So if I put in a -3, I get out a 3. If I put in a 1, I get out a 1. If I put in a 3, I get out a 1. If I put in a 4, I get out a -2. So for each given input, I know exactly what I'm going to get out. So this is a function. Students can often be confused by the double arrow. So in the last problem we had 2 arrows and it wasn't, and in this one it is. thinking about the vending machine, the difference is like this problem has two different codes that give you the same thing. And that's okay because, maybe M&Ms are really popular, so there's two different codes that would give you M&Ms. In this one, there's two different inputs, 1 and 3, that result in the same output. And that's okay for a function. But it's not okay if one input can make two different outputs. This problem asks us to graph the relation that was in problem 1. To do that, what we want to do is think of each arrow as creating an ordered pair. So I'm going to kind of redraw what we had there. We had inputs of -3, 1, and 4, which map to outputs of 3. 1 gave two different outputs, -2 and 1, and 4 gave an output of 4. I'm going to turn these into ordered pairs. So the first one is -3, 3. 1, -2, 1, 1, and 4, 4. Then I'm going to plot these points. This is our x-axis, and the vertical one is the y-axis. X comes first in the point and then y. So for -3, 3, I'm going to go back 3 spaces and up 3 spaces. 1, -2 would be over 1 space, down 2 spaces. 1, 1 would be over 1 space, up 1 space. And over 4, up 4. Now we said in question 1 that this was not a function, and now graphically we can also tell that this is not going to be a function by our vertical line test. If I drop a vertical line down here, I hit more than one point, which is not okay for a function. So that vertical line hits two different points, so that graphically shows that this is not a function. In this question, we want to graph our relation from number 2. So again, I'm going to rewrite the numbers in that problem as ordered pairs. So I give -3, 3 was the first arrow, 1, 1, 3, 1, and 4, -2. So I plot these then back to -3, up to +3, over to 1, up 1, over to 3, up 1, and over to 4, down 2. We said in question number 2 that this was a function, and we can see also that it passes the vertical line test. Anywhere I draw a vertical line, I only hit one point. It doesn't work for horizontals, but we don't care about that. All we care about is drawing vertical lines and making sure that we don't hit more than one point. Now, a few more vocabulary words here. An equation is how we represent a function with two variables, again typically our x and y. A solution is an ordered pair that makes an equation true. There are infinitely many of these. An independent variable is our input, typically our x. Our dependent variable is our output, typically y. We call it the dependent because it depends on what you plugged in. So you put in something, that's independent because you can put in whatever you want, and then the output depends on what you put in. A graph is a collection of points that are solutions. So how we graph is we make a table of values. We're going to use at least 3. We plot our points, and we connect the dots. Now you may have noticed I did not connect the dots in questions 3 and 4 when we were plotting those points, and that's really important because those weren't equations. They weren't a whole set of points. They were just a specific number of points. We had 4 points to plot, and that's it, and we don't know what happens between them. So if all you're doing is plotting ordered pairs, you do not want to connect the dots. When you're graphing an equation, then we want to connect the dots. A linear equation says that it has its highest power of x is just 1, so there's no x squareds. It's called linear because its graph looks like a straight line. Function notation is probably something that is going to be new for you. in Algebra 1, you studied linear equations and how to graph them. So that part's not necessarily going to be new, but more of a reminder. But this function notation is probably something that's new. Function notation is where we have this f and then an x in parentheses. It does not mean multiplication. It is not f times x. We read it as f of x, and what it means is I have some equation that I'm giving a name f, and x happens to be the input for that. We use this notation because then we can name functions all different things. So instead of just using x and y, then I would have y equals this, and y equals this, and y equals that. This way we can say f of x equals something, g of x equals something, h of x equals something, and we can be specific about different equations then. It also tells us what our input is, which is giving us some extra information that we have an input of x. To graph. You may remember from Algebra 1 some kind of shortcuts to graphing, and if you do, that's great. Feel free to use them. If you don't, that's okay. We'll be talking about graphing shortcuts in this chapter, and so I will reteach and remind you those. But for now, if you don't remember your shortcuts, what we're going to do is make a chart of values. I'm going to choose 3 x values. You can choose anything you want. I like to choose -1, 0, and 1 because they're nice and small, and that gives me kind of what's happening for different types of numbers. Then you plug them in. So if I plug in a -1 to the equation for x, I get -1 plus 1, which is 0. If I plug in a 0, 0 plus 1 is 1. And if I plug in a 1, I get 1 plus 1 is 2. Then I'm going to take these x's and y's and say that they are my ordered pairs, and I'm going to plot them. So I'm going to plot a point at -1, 0, a point at 0, 1, and a point at 1, 2. They should all be in a straight line. That's why I like to do 3 points, because if you only do 2, you can draw a line through any 2 points. But if you do 3 points, they should all be in a straight line, so that gives you something to kind of check your work. Connect the dots, put arrows on the end, because lines go on forever. There are infinitely many solutions to this. We found 3 specific solutions in our chart, but we could plug in anything. So this line goes on forever and ever. So to graph this one, I'm going to make my chart. I'm choosing to plug in -1, 0, and 1. Now to be pretty careful on this one because the equation already has a negative in it. So I'm going to plug in a negative, -1. Double negative really turns this into a +1, and I get 0. I'm plug in a -0 minus 1 gives me -1, and a -1 minus 1 gives me -2. Then I'm going to take these x's and y's and plot them as ordered pairs. So -1, 0, 0, -1, and 1, -2. And I connect the dots and put arrows at the end of that line. In these examples, we want to decide whether or not the function is linear, and then whether it is or is not, we want to plug in a value of x. We want to evaluate the function at a particular value. These problems have our function notation, so they have that f of x and g of x. Remember, it's not a multiplication, that's just naming the equation. To determine if our function is linear, we're looking, does it just have plain x's, no x squareds, no x cubes, no square roots, no absolute values, nothing fancy, just plain x's. There might be multiplication and addition, but no powers, no roots, no absolute values. So the first one here has an x squared, which means it is not linear. The second one has just a plain x in it, so that one is linear. Now we want to evaluate it no matter what. To evaluate the function at -2, what we're going to do is plug in a -2 for every x in the problem. being careful with parentheses. Then we are only going to do work on the right-hand side. I'm not going to do anything on that F side. So order of operations says I need to do these exponents here. That's going to give me a positive 4, and that negative out front's just hanging out. Then the multiplication, negative 3 times negative 2 gives positive 6. The 5's just hanging out. And then I'm going to add this all up, and that gives me 7. And it's done. We do not divide both sides by negative 2. Again, we do not divide both sides by negative 2 because that F parentheses X does not mean a multiplication. What this is doing is telling us I had an equation that was named F, I plugged in negative 2, and I got 7. So this notation tells us what equation we're talking about. It tells us our input was negative 2, and it tells us the output was 7. So this notation gives us a lot of information. For the G one, again, I want to plug in a negative 2. Do my work on the right-hand side, gives negative 4 plus 6, which then gives G of negative 2 is equal to positive 2. Again, do not divide out. This tells me my equation was G, my input was negative 2, and my output was positive 2. For our last two here, in the first one, we see an x squared, which means it is not linear. In our second one, we have a plain x, so that means it is linear. Then in this one, we're going to plug in a negative 3. So we replace all of the x's with negative 3's. Then we do our work on the right-hand side only. To get positive 9, minus 12 minus 1, and f of negative 3 is negative 4. And that's it. My equation was f, my input was negative 3, my output is negative 4. For the second one, plug in a negative 3. Do the work on the right-hand side, gives 9 plus 4, gives me G of negative 3 is equal to 13. So it tells me my equation was G, what I plugged in was negative 3, and what I got out was 13. Your homework is from 2.1. Make sure you notice on 36 to 48, you're doing multiples of 3 there. So 36, 39, 42, 45, 48.